The following program contains mature content which may not be suitable for all audiences. Viewer discretion is advised. This program is made possible by Genentech, dedicated to making a difference in patients' lives around the world, and by Cancer Treatment Centers of America, providing integrative treatment for over 25 years. By Siemens, a heritage of innovation, a passion for life. By David H. Koch. By Bristol-Myers Squibb, committed to the science of immuno-oncology. By the Alfred P. Sloan Foundation program to enhance public understanding of science, technology, and economics. By the Kovler Fund, pursuing solutions for America's neglected needs. By the Arthur Vining Davis Foundations. And by the American Association for Cancer Research. By American Cancer Society. By the Leukemia and Lymphoma Society. By the Entertainment Industry Foundation. By Stand Up to Cancer. By the Corporation for Public Broadcasting, and by the generous contributions to this PBS station from viewers like you. Thank you.
I sincerely believe that the time will come in my lifetime when we can control forms of cancer which are presently uncontrollable.
I try not to exaggerate, that we have found the right key. Now, whether it will open the gate into the secrecy of cancer, that remains to be seen.
If we can harness the built-in immunological system, I think we can lick cancer.
Again and again during the 20th century, scientists had convinced themselves that they were on the verge of a single cure for the many diseases called cancer. But with each breakthrough, cancer revealed new layers of complexity, and lasting cures remained tantalizingly out of reach.
It's like so many dreams that we have, where we can't quite reach something, where every time we grab something, it flies off like a ball in a pool, because it's constantly one step out of our reach, one step out of our reach. That is why cancer is like no other disease.
The new millennium would witness more frustration, more debate among researchers. But it would also see steadily deepening understanding of the ways cancer develops, of how it can be predicted and prevented, of how the body's own defenses can be arrayed against it. So many discoveries in so many fields that researchers have come to believe that real, durable cures are not only foreseeable, but inevitable.
The cycle of discovery over the last few decades has been incredible, and we're beginning to get a clue as to what the fundamental nature of the cancer cell is. And we're beginning to ask the question, can we now use that knowledge to launch a second attack, a more sophisticated attack, through prevention, through treatment, through targeted treatments against cancer?
The 21st century began with the promise of a new golden age of science, as enormous progress was being made towards solving some of the most challenging problems, from the AIDS virus to the origins of the universe. No realm of science seemed poised to make greater strides than cancer research. The discovery that cancer was a genetic disease in the mid-1970s had led to the first targeted drugs, which could, with pinpoint accuracy, strike at the very abnormalities that cause cancer. Herceptin, homed in on the effects of a single mutation, active in about a quarter of all breast cancers. But it was the next new drug, Gleevec, that especially caught the popular imagination. A simple pill active against a gene that causes CML, a deadly type of leukemia. Gleevec was the cure the cancer world had been waiting for.
You could take people with hundreds of thousands of malignant white blood cells, give them this drug, and within weeks, the disease was disappearing. Many people in the cancer community were saying, okay, cancer is going to be cured.
There is some new hope today in the battle against cancer.
This drug opens a door to the future.
Could this be the beginning of a revolution in all kinds of cancer treatment?
Gleevec becomes the new religion. It becomes the North Star of the cancer galaxy. And everybody, and I mean everybody, is suddenly focused on trying to replicate the Gleevec model.
If you look at the period between 2000 and 2005, it was truly extraordinary. We felt like we were in this golden age for cancer therapy. Major investments by pharma, by biotech, and it just felt like we were going to be off to the races.
But like so many promised revolutions in cancer treatment before, targeted therapy would have to overcome the cancer cell's uncanny resilience.
Well, extremely quickly, the question became, were those golden era drugs, Herceptin, Gleevec, outliers? Were they the exception and not the rule?
The discovery that genes caused cancer in the mid-1970s inspired a generation of scientists who decided to devote their careers to translating this insight into useful applications for patients. One of them was a young researcher at Johns Hopkins University named Bert Vogelstein, who set out to learn more about the mutated genes that gave rise to the disease. Vogelstein chose to focus on colon cancer, a slow-moving disease that would be easy to monitor over time.
Our idea was very simple. You just compare the DNA of a cancer cell to the DNA of a normal cell from the same individual and see where and if it's different. Okay, that's normal colon. This is what it should look like. And here's a colon cancer. If the DNA is different, then that's a very compelling argument that those alterations are responsible for the disease.
When Vogelstein began looking for mutated genes, the technology was primitive and the going was slow.
Logistically, one has to look through the literally billions of base pairs in a cancer cell genome to see what those differences are. And that was really the challenge back then.
By the end of the 1980s, after years of arduous work, Vogelstein had managed to identify not one genetic mutation in colon cancer cells, but several. He had also figured out the exact sequence in which these abnormalities occurred, a timeline of the cancer's evolution from one genetic mutation to the next.
In the parlance of cancer researchers, he created what we call the Vogelgram, a sequence of likely events that contribute to the development of a cancer. And it's not just one event. And you could begin to think about cancer as having a history.
Vogelstein's work really pinned down the idea that cancer, genetically speaking, is a multi-step process, not one gene for most cancers, but multiple genes that lead to cancer.
Vogelstein's results posed a series of challenging questions. Just how complex would cancer turn out to be? How many mutations would be found within the genomes of the major cancers, like those of the lung, breast, and pancreas? And how long would it take to find them all? The answers would begin to emerge from the completion of one of the most ambitious scientific projects ever undertaken, the mapping of every gene in the human body.
Today, the world is joining us to celebrate the completion of the first survey of the entire human genome. Without a doubt, this is the most important, most wondrous map ever produced by humankind.
The announcement of the successful completion of the Human Genome Project was a turning point for cancer researchers.
The Human Genome Project finally gave us a catalog of all the genes. The zip codes were all laid out. We had a complete Google Maps of the genome so we could navigate anywhere. And then when we had that, we could go searching systematically for all the genes that cause cancer.
Now that they had sequenced the DNA of normal cells, researchers believed they could do the same for cancer cells. Then, to find the mutated genes that trigger cancer, all that would be needed would be a side-by-side comparison. The genes of normal cells next to the genes of cancer cells.
Unlike in the past, where you were looking gene by gene, one by one by one, you can now look at the entire spectrum. You can look at the landscape, as it were, of cancer. And you compare, within the same individual, the normal genome, not one gene, but every single gene, with every single gene that's altered in cancer.
Though it seemed simple, this idea would spark a massive international effort beginning in 2005 to collect, sequence, and analyze thousands of samples of the most common cancers. It was called the Cancer Genome Atlas.
The Cancer Genome Atlas was an incredible team science effort where this group got together and said, we need to understand the atlas, the landscape of all of the genetic changes that can happen in cancer, to understand what is the possibility of what can go wrong.
By the spring of 2008, the first results from the atlas were ready.
The most exciting meeting was that first time where there were enough samples from brain tumors to be able to begin to say, okay, what's new here? Previously, you've had only a blurry view through the fog, and you could make out some of the most dramatic features. But now the fog's blown away. You can see the whole landscape of what's there and infer truth about how those cancers happened.
But as more and more results poured in, some of the initial excitement was replaced by anxiety. There could be no doubt that what Vogelstein had glimpsed in colon cancer was just the beginning.
The profoundly surprising thing about the Cancer Genome Atlas is that pointed out that cancers are much more genetically complex than 3, 4, 5 genes. There can be 10 genes that are altered, 20 genes. In one breast cancer specimen, 110 genes were altered.
Even more confounding, the majority of genetic abnormalities discovered were not familiar oncogenes, but another type of gene called a tumor suppressor gene. Unlike oncogenes, which tip cells into a frenzy of cell division, tumor suppressor genes, when damaged, fail to stop cells from dividing.
Tumor suppressor genes are, in a sense, the opposite of oncogenes. Oncogenes kind of work like an accelerator in a car. They drive the cell's growth, and the tumor suppressor genes are the brakes. And in many cases, the brakes are simply gone from the cell.
We now realize that virtually all human cancer cells have both defects: stuck accelerator pedals, hyperactive oncogenes, and defective tumor suppressor genes, defective brake linings. And together, those two defects conspire to make the full panoply of abnormal behaviors that we associate with malignant cells.
In the span of a few years, as the true complexity of the cancer cell became clear, any hope that targeted therapies would win a quick victory over the disease was dispelled.
The cancer genome is exceedingly complex. Each cancer type contains anywhere from 50 to 100 recurrent amplifications and deletions. So while the progress over the past 20 years has been impressive, it's also clear that we are dealing with the tip of the iceberg.
The discovery of cancer's complexity during the century's first decade seemed to push cures even further away. Drug developers could now see the genetic landscape of cancer more clearly, but the picture was one of intimidating chaos. However, there were still a few cancers that seemed to be caused by just one or two mutated genes. It was on these that drug makers began to focus most intently. In 2003, scientists working for the Swiss giant Novartis believed they had found a likely target, a rare oncogene called ALK. Japanese researchers had shown that a mutation in the ALK gene seemed to be the cause of a type of lung cancer that affects around 40,000 people a year worldwide. Though the market would be relatively small, Novartis decided to pursue a drug targeted against this mutation. Their scientists began by manipulating various compounds to try to block the effects of the gene. After 7 years of trial and error, they believed they had one that might work.
You see, yeah, it really looks like this. We have room here, right, to put something that could fill the pocket better, something larger, yes.
The drug, called LDK, works by filling a pocket in a protein inside the cancer cell, blocking a stream of growth signals produced by the mutated gene. It's like jamming a lock with a broken key.
It's a beautiful compound. It's actually beautiful when you see it fit into the pocket. It's really designed to do what it's doing, the job it's doing.
Everybody thinks their baby is beautiful. The medicinal chemists have a very tough challenge. Not only do they have to find a molecule that fits that pocket perfectly, they also have to simultaneously be making sure that the changes they make in the molecule don't cause it to bind to something else and cause toxicity. And so the best analogy I can think of is it's like a Rubik's Cube. You can solve one side of the Rubik's Cube, and it's all blue, and it fits into the enzyme perfectly, but you've messed up all kinds of other things, and maybe it binds to something else that causes toxicity.
The chemists need to be eternal optimists, because 99.9% of what you do fails. And after years of work of hundreds of scientists, it all came down to one powder right here in the vial.
So I take 4 of these every day, and this is what's keeping me alive, literally.
In 2013, Dr. Juan Manuel Gomez, himself a physician, became one of the first patients ever to take LDK.
Oh, they are calling for me.
Hi.
This way?
Yep. All right. We're gonna take a left.
Gomez had been told that his prognosis was dire. His lung cancer was inoperable and chemotherapy was no longer an option. With nothing else to try, his doctors urged him to join an early trial of the LDK drug.
Move your shoes and step right up on the scale.
All right. It was very clear to me if I didn't do anything different, you know, I was not going to be here. You know, I was dying. I was. I mean, I knew. I could feel it.
The drug had an immediate impact. Within weeks, Dr. Gomez's tumors began to shrink, and he was able to resume a normal life.
I think advent of these targeted therapies really has been miraculous for some of our patients.
So can you unbutton that top button for me?
The disease melts away, something that chemotherapy could really never do.
Couple deep breaths.
And when I'm saying amazing response, I'm talking about these images full of cancer with blotches pretty much throughout the lungs. And these patients would be treated with this drug, and all these patches would now just disappear. Even more, I think, stunning for us as oncologists is that patients would feel better very, very quickly.
Well, your labs look perfect today, so that's great.
Excellent. Yes.
And your scans look great too. So I looked at the chest and the abdomen and the brain, and they look beautiful.
No, I think you're doing great, side effect-wise.
But even with drugs like LDK that show early promise in clinical trials, there is a problem. Most soon stop working. The reason why comes down to a concept familiar from infectious diseases: resistance. Even if a drug can shut down the one key mutation in a cancer cell, the cell often mutates again and is no longer vulnerable to the effects of the drug.
Cancer cells are constantly mutating. In fact, the cancer itself is evolving inside your body over time, so that the genetic diversity of cancer at week 0 is not the same as the genetic diversity of cancer, 5 years or 10 years from now. It transforms the idea of treatment from a static idea to a dynamic idea.
Scientists had long understood that cancer was not the same disease in everyone. But with the realization of cancer's mutability, they now feared it might not be the same disease in anyone.
What we know today is that each cancer is a moving target, and very few drugs, even when they're having fantastic clinical results, end up curing people because the cancer becomes resistant to the drugs that we're using in almost every case.
As a doctor himself, Juan Manuel Gomez was aware of the possibility that his cancer would become resistant to LDK.
It is a gamble. I mean, they don't know. They probably have seen some results in some animal models, and they know the drug works. Is that going to necessarily translate into a human being? No one knows.
In fact, just 6.5 months after enrolling in the clinical trial, Gomez's cancer did become resistant to the drug, and he was forced to try another experimental therapy. That therapy also stopped working, and Dr. Gomez passed away in October 2014. Gomez's experience on the LDK trial was not exceptional. When all the results were tabulated, the drug had extended the lives of all 160 patients by an average of just 7 months.
The successes of the first decade of targeted therapy were so enormous that when the second decade started rolling around, all of a sudden we felt disappointed, because rather than having Gleevec, we were getting incremental advances.
In the last decade, an average of only 4 new targeted therapies have been approved for use in patients each year, most of which have extended patients' lives by just a few months. 9 of 10 new experimental compounds fail. This incremental progress has come at a high price, billions of dollars in research and development. To recoup these costs, pharmaceutical companies have priced their successful cancer drugs at unprecedented levels.
The reality is, for the overwhelming majority of patients and oncologists, this is one of the biggest problems in cancer care. If you look at the prices of cancer drugs, before the year 2000, the average price was about maybe $5,000, $10,000 a year. And then in the year 2012, 12 of the 13 drugs that were FDA approved came at a price of $100,000 or more.
At the Charleston Area Medical Center in West Virginia, staff oncologist Dr. Suzanne Cole sees the impact of the high cost of cancer care every day.
Hello, how are you today?
I'm doing great, and I didn't know you was...
Yes, I'm having a baby.
Oh, congratulations.
It's not gonna be too long from now. Some of our patients who are, middle-class Americans working normal jobs with awesome insurance, sometimes that insurance doesn't, cover everything that's necessary, and there are significant medical bills month to month to month to month. All right, so what I'm gonna do is give you a standing order for labs. And I just want you to keep this in your purse. And if you're on a medication that you need to stay alive, and your copay on that medication is $700 a month, that's rent, that's a car payment, that's, You know, that's a crazy amount of money to be forking over every month just to have access to the thing that's going to keep you alive.
Ms. Carrington, this is Jennifer Bass.
Hi there, nice to meet you. Nice meeting you.
She is our financial navigator, and she helps people in your situation get back on track with their insurance so that they can get their cancer treatment.
Okay.
At the Charleston Hospital, a full-time employee helps patients who have no ability to pay their medical bills.
I appreciate it.
Yes, ma'am. I'm going to give
Thank
you all of this. You fill out once you start getting bills.
Okay.
Don't pay any of them.
No,
Don't get
no, I can't.
Don't pay
I'm
any of
not
those.
working now.
This is this year's patients. This is what I have worked with this year on some form of financial assistance. It is completely full. I have ostomy supplies up here. I have mastectomy bras and mastectomy prosthesis up here. This is a blood thinner. I think there's a wig under my desk. Yeah, I stick things everywhere. Wigs, whatever it is, I will take it.
Getting cancer is one of the worst economic things that can happen to you in the United States. It causes the accumulation of enormous amounts of debt, fundamentally shifts the finances of families, and what's very challenging for a lot of patients is that it can often be a disease that ends your life. And so sort of the resources you've accumulated that you hope to pass on to your heirs or your surviving spouse or someone else end up being consumed in the treatment of a condition that in some cases is incurable.
The impact of the high cost of drugs is most acute in the United States, where drug companies set their prices. In countries where the government negotiates those prices, fewer patients choose to forego their medications rather than pay for them. In the developing world, new cancer drugs are often not even available because their cost is so high.
This is a moral issue. There's a 10 to 15% lower 5-year survival in cancer in people who are uninsured, and in people who are poor, and in people who are black. People should not die because they're poor. People should not die because they're uninsured.
The solution to the problem of cost, many believe, lies in understanding even more about the mechanisms of cancer, so that so much money is not wasted in pursuing flawed drugs.
This whole system is extremely inefficient. We are not choosing the targets appropriately or wisely, and therefore all of these medicines are failing. So what we really need to do is to perform more efficient research, and really it needs to perform more efficient basic research, and that's what's going to drive down the price of cancer drugs.
And yet, funding for the most promising basic research has not been so tight since the National Cancer Act was passed in 1971.
As the director of the National Institutes of Health, I live with the reality that we're not limited by ideas, we're limited by resources, and we're not going as fast as we could. We are now about 25% below where we were 10 years ago in terms of resources to do this work. We've got to figure out how to turn that around.
$511.53.
Until better and cheaper therapies are discovered, many patients and their families are forced to make a difficult calculation.
What am I willing to pay for how many months of life? You know, how do I think of that? What equation governs, 3 months of life for X $1,000?
Maybe it allows somebody to see a grandson's birthday party or to go to a wedding. Those are great moments of life. So maybe that's enough, I think it's not enough for most people, and especially given the amount of effort that we've put into this problem.
With so few new targeted therapies, treatment at most cancer hospitals around the country remains much as it has been for the last 20 years.
Everybody is so excited about all of these new targeted therapies, but when it comes down to it, the vast majority of most of the cancers that we take care of
they are still primarily treated with chemotherapy. There are cancer surgeons, there are radiation oncologists, but the backbone of what we do is we give chemotherapy.
Chemotherapy has gotten better over the years. By using these drugs in combination and tailoring them more effectively to each patient, doctors have made inroads against many cancers. Of all patients who will be diagnosed this year, some 2/3 will survive over 5 years. And of those, many will go on to live normal lifespans.
There are a lot of tumors that we take care of that are cured. Early stage breast cancer, early stage colon cancers, early stage prostate cancer. Many of those patients will live the whole rest of their lives and never have any problems ever again.
Hey, how's it going?
Dr. Cole sees up to 25 patients a day. Many will be able to live with their cancers for years or see them disappear entirely.
Dun, dun, dun. It's 8.2. Oh my God. Yeah, I know. It's like the best it's been.
But those she spends most time with have relapsed or been diagnosed with metastatic disease.
Are you better than yesterday?
Oh gosh, yes.
And for them, she must offer a very different kind of care.
I know going into this that the vast majority of my patients who come to me with stage 4 disease are going to die. And there's nothing that I can do about that, end fact, because it's the nature of the disease that they have in the times that we live with the tools that we have.
Any weird headaches, blurry vision? Nothing.
It's very hard to talk about death to somebody who's in relatively good health. You know, somebody who's just been diagnosed with a cancer, they may not even feel it inside of them. And you have swollen lymph nodes all along that area, and there's one that's kind of higher up that I'm worried about. Right. But if they're in a situation where it could happen, they need to know that that's a possibility. And I just believe in that core principle so deeply that it really guides me in how I talk to every single one of my patients. Tell me what you know about your lung cancer.
I have just really known for 3 days that I have cancer.
Okay.
I was just diagnosed.
So what was wrong? I remember as a resident rounding with lots of fantastic physicians who would walk into a room with a patient. They would say, everything is fine. You know, you're getting better. You'll be getting out of the hospital soon. And then we walk into the hall. We walk a few steps away from the door, and you know, very casually, oh, you know, that guy's not long for the world. And why should we as physicians have all of this information about the patient? It's the patient's information. Are you interested in knowing numbers about your prognosis? Are you interested in that kind of thing, or are you too overwhelmed with all of it to...
Yes, I'm the type of person that likes to know as much information as possible.
When we're dealing with a stage 4 lung cancer, we know that it is not a curable situation. It is treatable, and we can do things to intervene and help you live as long as possible. But because this cancer has spread through the body, it's much more likely that this cancer is going to be the thing that takes your life rather than something else.
Well, you gave a deeper explanation than I had heard earlier today, so it's pretty...
It's really incredibly hard to sit down with another human being and look them in the eye and say, I'm sorry, but there's nothing more that medical science can do to make you live longer or better.
I wish that we had some magic medication that would make this all disappear. All of the treatments are to give you as much time as possible.
Most cancer is very predictable. Once it comes back, unless it's a curable disease, of which there are a number, it's going to be the end of that person. And there are certain tasks that the person should do before they die.
And that's just being, you know, as straight about it so
Which I
that
appreciate, yeah.
you have a good sense of what you're really dealing with, and you can make the best choices in the context of your life. knowing that we might be on limited time.
Well, this just really sucks.
It does. And I'm sorry.
Yeah, me too.
If you're hearing about that 4 weeks before you die, you're probably not going to have a chance to go to LA and make up with your brother out there. You may not have a chance to talk to your priest or rabbi at a time when you're really well. And all of that can be helped by just being more honest with people during the course of their illness.
I just hadn't been focusing on it.
All the data suggests that directly addressing symptoms, relieving their pain, keeping them more functional, allows them to live a longer period of time as well as a better period of time.
Been trying to do what I want to do, you know, live life to its fullest and to enjoy it. Well, it has a different look on it for the next couple of years, I think.
Yes.
Dr. Cole's approach is relatively new. For decades, so-called palliative care was almost taboo in oncology. The focus of cancer treatment was on eradicating tumors at all costs. Doctors did little to alleviate the pain or address the psychological needs of dying patients.
To many doctors, the word palliative care was a word that they were allergic to because it meant that telling the patient, but perhaps telling themselves more than anything else, that this was defeat. Obsessed with cure, this voice of palliative care, restoring patient autonomy, restoring patient dignity, it was pushed away into the background.
The movement toward palliative care began in the 1960s in London, where a British nun named Cicely Saunders set up a clinic to care for patients at the end of their lives.
We certainly owe a lot to Cicely Saunders. She showed that one could make the life of people who are dying much more comfortable with adequate pain medication and with adequate emotional support. And she began to talk across the country to nurses, oncology centers, and had a real impact on palliative care beginning in this country.
Today, palliative care is part of the medical training and everyday work of more and more oncologists and oncology nurses in the United States.
Do you feel like at this point, after everything that you've gone through in the last couple months, and we were to have to really think about chemotherapy, you'd be wanting to do that again, or you're not sure?
I'd probably be wanting to.
You'd be willing to try it?
Yeah.
Okay.
Some people, they need to do everything that they can do that is possible to be done to stay on this earth.
They can still say, I love this life. I love being alive. I love being here, and I will do anything to stay.
For some patients, it is a war. Their experience of it is a war, and to say that it isn't is to deny them their reality. It is a war for them. And yet for other patients, they don't want to fight. But it's not the language of defeat. It is the language of negotiation. It is the language of what to do next, given the circumstances.
So, you've been in the hospital for a couple of days, and you know, one thing that I just wanted to make sure was that you were understanding what was going on with your cancer. We've done some chemo, and it seems like it's not really helping us slow down the cancer. And so we're gonna have to make a choice about whether you wanna try to do more treatment or whether we should stop.
He wants to do whatever you think is best, right? Because you trust her 100% with everything. And we don't know, so we're gonna leave it in your hands.
Okay. Right now, your body is in a situation where we've got to get you better before we could even think about doing more treatment, you know? But it's not a bad choice to sometimes say no to the chemotherapy and take what time that you have left and enjoy it and not be sick and coming back and forth.
I see the time coming. but the life you give me already is better. Thanks.
I just really want what is best for you. I want you to feel well for as long as possible. You know, I want you to be free of pain, and I don't want you to struggle at all. We're gonna just focus on trying to help you get stronger so that you can get out of the hospital.
Yeah, thanks.
And once you're home, we can talk about, you know, whether it makes sense to do any more treatment or not.
Right.
And if we decide not to do it, then I'm gonna have hospice come and be with you, okay?
Okay.
You're doing good. You're hanging in there.
I don't know if everybody has the same opinion of what is a good death,
All right, sweetie, I'll check on you tomorrow.
but I think that it might be better for someone to maybe be in a place that they're comfortable, surrounded by people that they love. If you decide to pull back from treatment and go on hospice, then you have some say about how you die and where you die and who is with you. As oncologists, we may not be curing everybody, but we are helping people in a very important way.
You good for right now?
Healing is not always eternal life. You know, healing is sometimes helping people have a good death. There's some kind of healing in that too.
There's an often noted paradox that we must now honestly confront. Namely, despite the extraordinary progress we've made in understanding the underlying defects in cancer cells, it has to be acknowledged that we have not succeeded in controlling cancer as a human disease to the extent that I believe is possible. Now, I know other
As the first decade of the 2000s passed without the expected revolution in targeted therapy, some prominent voices in the cancer community began to call for a shift in priorities, from the costly hunt for new drugs to cancer prevention.
If you don't get cancer, you're not going to die from it. And that's a simple truth that we sometimes overlook because it's intellectually not very stimulating and exciting. Persuading somebody to quit smoking is ultimately a behavioral, a psychological exercise. It has nothing to do with molecules and genes and cells. And so people like me are essentially uninterested in it, in spite of the fact that stopping people smoking will have vastly more effect on cancer mortality than anything I could hope to do in my own lifetime.
Prevention, blocking the factors that cause the disease in the first place, had long been the forgotten front in the war on cancer. But as prevention advocates began to gain a stronger voice, they could point to some important successes. None more so than the campaign to stop smoking.
Cigarette smoking contributes substantially to mortality from certain specific diseases and to the overall death rate.
The anti-smoking campaign began in 1964, when the Surgeon General definitively linked smoking and lung cancer. At first, the finding had little effect. The rate of smoking increased in 1964, 65, 66, and 67.
Tell me, sir, it's been 4 years since the Surgeon General's report came out about smoking and cancer, and you're still smoking. Why?
Because this is a long-standing habit of mine. Regardless of what these doctors say, a lot of people will not pay much attention. There's other things more dangerous than smoking.
It would take a much more imaginative strategy to finally begin to curb America's addiction to cigarettes. The idea was the brainchild of a 26-year-old patent attorney named John Banzhaf. It involved turning cigarette companies' reliance on television advertising against them.
Marlboro, the cigarette with better makings, brings you pro football.
It was Thanksgiving Day. I'm sitting there with my father. We were watching all of the football games, and just over and over and over again, you see cigarette commercials, cigarette commercials, cigarette commercials. Now, I'd seen hundreds, thousands, tens of thousands growing up, but just something clicked.
There's always time for a Marlboro.
Something occurred to me, something I had learned in law school, which is called the fairness doctrine, which said that if you present one side of a, quote, controversial issue of public importance, you must make reasonable time available for the other side. And it occurred to me, could that possibly apply to cigarette commercials?
Banzhaf wrote a letter to the Federal Communications Commission demanding that the television networks air anti-smoking messages alongside cigarette advertisements. To his surprise, the FCC agreed.
So the American Cancer Society produces a set of striking anti-tobacco ads in the late 1960s, early 1970s.
It's all yours. Your total consumption of cigarettes so far, George, 500,000.
And although they're often shown by networks late at night, they begin to have an impact on rates of smoking.
There were people coming up to me and saying, I quit smoking. My father quit smoking. And then suddenly, their ads become a liability. The more they advertise, the more people stop smoking. They had to get off the air.
In January 1971, the last smoking ad appeared on American television. Anti-smoking advocates would eventually persuade all 50 states to regulate cigarettes more heavily and sue tobacco companies for the health care costs of smoking.
Paid $250 billion. We killed off Joe Camel. We got rid of cigarette billboards. We're the model. We're the example. We did it, and we did it against these tremendous odds.
From its height in the late 1960s, cigarette smoking has declined by nearly half. As a result, lung cancer has also begun to trend downward.
Almost nothing has saved as many lives, reduced as much suffering as our recognition of the fact that smoking causes cancer.
Another preventable epidemic now threatens to spread the disease. Though no one is certain of the mechanism, obesity clearly conveys a higher risk of colon, breast, and kidney cancers, among others.
It's predicted that as smoking rates continue to slowly decline and as obesity rates continue to explode, that before the end of this decade, that obesity will pass tobacco use as the leading preventable cause of cancer. Anti-smoking campaigns have been around for a while and have been very successful, but we still have not turned around the obesity epidemic, which at some point we're going to have to face square on and fix.
After smoking and obesity, however, the known preventable causes of cancer have been much harder to find. Radiation, sunlight, asbestos, a few viruses, all have been proven to trigger the genetic mutations that give rise to cancer. Still, it is estimated that some 40% of cancer cases have no known cause at all.
The work on what causes cancer is the most difficult form of cancer research at the moment. We don't know the cause of most of the major killers. We really don't know what causes breast cancer, pancreas cancer, colon cancer, prostate cancer. We don't know what causes them. The way we know that if you stop smoking cigarettes, you can reduce your risk of lung cancer.
Many of the mutations that cause cancer are probably the result of accidental copying errors among billions of cells that divide every day. But for decades, scientists have searched for hidden triggers in the environment that might explain those cancers that yet have no explanation.
We live in an increasingly carcinogenic environment. This could be causing many cancer deaths. Scientists have been testing nearly every substance known to man to track down carcinogens.
With so much mystery still surrounding the disease, a series of unproven theories about what causes cancer have been paraded through the media. Everything from sugar to plastics, high-tension power lines to cell phones. But proving a causal link between any agent and cancer is difficult, and this fact has greatly increased anxiety and fear.
Cancer is frightening, bewildering, frustrating. Many people are just endlessly trawling over, trying to figure out, what did I do? Where did I go? Should I have taken that vacation? Was I near a nuclear reactor? You know, did I drink some water? Did I not eat organic foods? And you're saying, look at all these scientists who claim to know so much, and they can't explain to me why this individual, developed lymphoma, leukemia, or breast cancer.
Unable to identify the causes of many cancers in the laboratory, a branch of science called epidemiology has approached the problem from the other end. By studying the incidence of cancer in contained populations and working backwards toward a common cause.
It is very much like circumstantial evidence in a court case. An epidemiologist, much like a lawyer, is trying to figure out, often based on retrospective data, on reconstruction, what the true set of events might have been that caused cancer.
One of the first epidemiologists was an Italian physician, Bernardino Ramazzini, who in 1700 associated many diseases with occupations. Goldsmiths developed mercury poisoning. Coal miners suffered lung disease. Ramazzini's observation that childless nuns had higher rates of breast cancer laid the groundwork for understanding the role of hormones in the disease. In the 18th century, doctors noticed that habitual users of snuff had higher than normal rates of nasal cancer. In the 1950s, a concentration of rare lung cancers in shipbuilders would lead researchers to asbestos. But more often, epidemiologists have struggled to understand the behavior of cancer. Why do some cancers appear more often in some countries than in others, even among people who recently moved there? Why do cancers sometimes seem to act like infectious diseases, breaking out in small populations called clusters? Cancer clusters have been particularly controversial. Famous examples, like those at Toms River, New Jersey, Woburn, Massachusetts, and along Love Canal in upstate New York, have frustrated investigators and led some to doubt that they were anything more than a statistical mirage.
Cancer clusters are extremely difficult because the numbers are very small. You often go to investigate the cluster some years after it's happened. Now it's gone. Circumstances may have changed. The point source of whatever it was, if there was something, may have disappeared. So it's an incredibly, to do the detective work here is really extremely difficult.
Nobody knows how many clusters there are and how many of them are really related to some common cause. Our tools just aren't powerful enough, aren't good enough. It's sort of like going into a gigantic dark warehouse full of dangerous objects with this tiny little miner's lamp on your head and going in and looking around and say, gee, I don't see anything, right? And then going out again.
But even as new chemicals that cause cancer have been difficult to find, an old suspect has reemerged: viruses.
For a number of cancers, some very common ones like liver cancer and cervical cancer, viruses are front and center in the major causes of those cancers. Happily, we have developed vaccines that can prevent infections with some of those agents, and that has reduced the incidence of cancer dramatically.
Tonight we have some news we do not get to report often enough in the battle against cancer. The first large-scale test of a vaccine for cervical cancer found the drug 100% effective in blocking the virus that causes the disease.
A vaccine approved by the FDA in 2006, active against the human papillomavirus, the leading cause of cervical cancer, promises to all but eradicate the disease if children can be inoculated before they become sexually active.
When I was a resident, if you had an abnormal pap smear, you had a total hysterectomy because we didn't know what else to do. You lost your fertility. And then we figured out that it was caused by a virus, and now we have a vaccine. So my daughter's been vaccinated. Now that's amazing. That's pretty amazing. We essentially can wipe out cancer of the cervix by the HPV vaccine.
The science of cancer prevention is still young and dependent on imperfect knowledge of what causes cancer. But even if it succeeded only in curtailing smoking, obesity, and the known cancer-causing viruses, it would have a profound impact on mortality.
It has been estimated that today, if society were to implement what's known about prevention, then cancer deaths could be reduced by 50%. And that's without any new research or any new discoveries. It's just implementing what is already well known.
Here's my cherry-flavored New Lightly. Looking forward to drinking this in the next several hours.
Even when cancers can't be prevented, they can still be stopped if they are detected early enough.
Bottoms up, so to speak.
In March 2000, 2 years after her husband's death from colon cancer, TV anchor Katie Couric began a well-publicized crusade to increase the number of people getting routine colonoscopies, which can detect the disease in its earliest stages.
So far, I'm looking pretty clean, huh?
Very clean. People don't wake up one day and all of a sudden have a cancer. If you have this giant window of opportunity, 20 or 30 years, to catch a cancer before the final stages, which only occurs in the last few years of this long lifetime of the cancer, and they can almost always be cured by surgery alone if they're caught early.
Okay, Katie, that's it.
That wasn't bad at all.
No.
In the last decade, partially as a result of Couric's efforts, colon cancer screening is up sharply, and mortality from the disease is down nearly 10%.
The full examination requires 3 views: the craniocaudate view, the medial lateral view, and axillary view.
In the 1950s, a doctor at the MD Anderson Cancer Center in Houston invented a method of taking detailed images of the inside of the breast.
The head is turned to the contralateral side. The tube is then swung into place.
The mammogram was hailed as a major breakthrough in the fight against breast cancer.
This is a finished product. Note the second carcinoma within this breast, not appreciated clinically.
Over the years, with the help of an activist breast cancer community, the test became part of millions of women's annual checkup.
Every woman in America over 35 should know this word, mammography. It's a fast and simple procedure that can detect breast cancer early while it's highly curable.
We have pushed for mammography screening for once a year for a lifetime. Early detection saves lives. Whole organizations were built around that concept. The breast cancer industry was built around that concept.
But like so many cancer therapies or prevention methods, the mammogram has turned out to be too blunt an instrument for the complexity of cancer. A bevy of recent studies have shown that while annual mammograms result in a clear reduction in mortality for women over the age of 50, the benefit to younger women is negligible. In these earlier years, the test is too imprecise to distinguish a real cancer from a harmless growth. Meanwhile, false positive diagnoses have led thousands of women to undergo painful, expensive, and disfiguring treatments like mastectomy.
In breast cancer, we're so afraid of missing that one patient in 1,000 that will die of the disease, we end up treating all 1,000. So that triggers enormous amount of procedures, treatments, interventions that is difficult to stop. It's ethically difficult to stop, and economically it's difficult to stop because the incentives are to sustain it.
Men have not been spared the collateral damage caused by an imprecise method of early detection. Like the mammogram, the test for prostate cancer, the prostate-specific antigen, or PSA, is often misinterpreted, leading to high rates of false positives and unnecessary surgeries.
The difficulty that's faced by the patient is saying, is my early abnormality harmless, or is it going to be harmful? Will I regret not proceeding? And that's a very difficult choice because the consequences of being wrong can be devastating.
There we go, right there.
What we're all looking for is, can we find markers that say, yes, there's some abnormality, but the likelihood of this developing into a frank cancer is extremely low.
These markers, or clues to the presence of cancer, might come in the form of mutations that turn up in routine genetic screenings.
It's our hope, maybe our dream, that one day when people go to their yearly office visit and deposit samples of blood and urine, etc., these specimens will be tested for mutations. They will be alerted to the presence of a cancer which they wouldn't yet know about because it hasn't caused symptoms, and they can then be handled through surgery, and the cancers are gone. That's the hope.
CCC, TCTCA.
Already, there are a few tests that can detect genetic mutations that will likely give rise to cancer before a single cancer cell has even appeared in the body. The first grew out of the work of a young biologist named Mary Claire King, who in the mid-1970s began investigating why there were some families in which breast cancer was much more prevalent than in others.
I said, this is a common illness. How much breast cancer would we expect to see clustering in families just by chance, because it's common? And then how much more or less than that do we actually see?
King discovered that in some families, the rate of breast cancer was so high it could not be by chance. She hypothesized that these families must carry a genetic mutation that they pass down from one generation to the next. To prove that there was a gene, and then to find it, King was going to have to work closely with affected families.
I needed families who would be part of this, who would be patient, and who would be willing to have me come back to them and talk to them over and over and take blood samples and ask to collect the tumor samples when they had surgeries and would listen to my hypotheses and talk to me forever.
There was one man she knew who could help her find such families. Dr. Bernard Fisher was by that time in the midst of his groundbreaking study on the effectiveness of the radical mastectomy. If anyone could introduce King to families with inherited breast cancer, it was he.
Meeting Bernie Fisher changed my life. He knew from his practice that these families show up from time to time, and he knew that when he was working with a family that had had historically in generations, 4, 5, 6 cancers, he was sure that in the next generation it would show up again. So when I asked him if he would help me identify families, he said, "Oh, of course." On this pedigree or family tree, circles represent women, squares represent men, and filled symbols represent cancer.
Working in this way, family by family, King was able to identify the section of DNA along chromosome 17, where the mutated gene was found. The gene was called BRCA. Women who carry the BRCA mutation, which can be detected by a simple blood test, know they have up to a 70% chance of contracting breast cancer and a 30% chance of developing ovarian cancer. With this forewarning, they can take preventative measures. They can watch themselves more closely or choose to have their breasts removed before cancer ever appears. By knowing much more about how cancer develops, doctors may be able to assess the risks for each person long before he or she contracts the disease and develop strategies to prevent it or detect it early.
I think the time will come where your own individual risks are going to be better predicted by using your family history, by using your own sort of environmental exposures and your lifestyle, and by using your DNA. So here's not looking at a cancer genome here, looking at your constitutional genome and saying, okay, for you, your risks of this disease are higher than the average, for that disease are lower. Clearly, if we're talking prevention in a way that's going to work, it can't be one size fits all. It's got to be focused on that individual.
The combination of prevention, early detection, and some new targeted therapies have made a significant difference in the fight against cancer. In the United States, cancer mortality has been slowly declining, down 20% over the last 2 decades. And there is optimism that this trend will accelerate. One major reason is that researchers have begun to discern patterns within the complexity of the cancer cell that once had seemed so daunting. The first step was understanding that not all the mutations in cancer cells are equally significant.
Most mutations in a cancer cell are random, unimportant mutations. There's a limited number of those changes that really confer the properties on the cancer. What we have right now is a sifting process to find, by comparing many different cancers, which ones are the recurrent targets that really matter and give the cancer its properties.
Those mutations that are significant, it turns out, often play a key role in many different cancers.
In fact, a breast cancer and a leukemia, which look completely different under the microscope, may actually share some altered genetic components. So therefore, the world of cancer, having been diversified, now begins to find these, I can only describe them as sort of genetic wormholes, from one cancer to another.
These fresh insights have rejuvenated the field of targeted therapy. If the many mutations in a cancer cell can be narrowed down to just a few, blocking their effects might be possible with a technique already used, in a much less precise way, in chemotherapy: combinations of drugs.
The key is to hit a cancer with multiple drugs simultaneously. When a cancer mutates, it gains some new properties. But very often it gains a new vulnerability as well. It gains a power and it gains an Achilles heel. So what's exciting right now is in cataloging for every mutation the Achilles heels it creates. If mutation here, vulnerability there, attack there. Might mutate, but you've also got over here to hit. You're laying out essentially a way to deploy your armies, knowing that cancer is going to try to escape down this path, and you've got something waiting for it.
Not only have cancer researchers narrowed down the number of oncogenes and tumor suppressor genes that actually cause cancers, they've also discovered that none of these genes operates in isolation. Instead, they work as part of groups called pathways to accomplish specific tasks.
There are only about 200 genes which are responsible for the vast majority of cancers. Then these 200 genes funnel down into only about 12 pathways. If you can figure out a way to target these pathways, you will have a therapy that's useful for many different kinds of cancers.
You can think of a pathway like a circuit or a bucket brigade. If you disrupt the bucket brigade at any one number of positions, you could disrupt the entirety of the brigade. What we're learning now is that there may be multiple different ways to activate this bucket brigade causing cancer, but it also means that there are multiple places to intervene and disrupt it.
Make no mistake, this is complicated. It's at least as elaborate as the most complicated electronic circuit diagram that you have ever seen. But getting our minds around that, even if it's somewhat imperfect, offers a lot of opportunities.
With the cost of genetic sequencing plummeting, it may be only a matter of time before doctors can map all the genes and pathways inside every patient's cancer and treat each of them with a personalized combination of drugs.
Where we're going is this much more individualized approach, just like infectious diseases. If you have a very bad infection, very bad, your doctor will take a sample of the bug, grow it, and pick an antibiotic or two, or sometimes three, mix them together and hopefully cure you. And that's what we're trying to do in oncology now.
No matter how powerful or precise, however, combination targeted therapy still must confront cancer's complexity and its relentless drive to adapt and survive.
To me, the best way to think about cancer is that it is literally evolution in a bottle. It's like taking the enormity of the power of 3 billion years, unimaginable time frames that have created the unimaginable diversity of life. Imagine capturing all of those forces within a single cell and putting that inside someone's body. That is, to me, the metaphor of cancer. It is all of the history of life that plays out at 1 billion times the speed of evolution.
If cancer exploits the power of evolution to survive, perhaps only a commensurate weapon, equally adaptable and also perfected over millions of years, can overcome it. That weapon, many scientists believe, is the human immune system.
The immune system is an extraordinary set of defenses, an intricate interplay of cells and proteins. They're circulating through our bloodstream. They have these surfaces that keep looking and saying, is there something foreign? Is there something changed? Is there something different? Because I have to keep that out.
The idea that the immune system might effectively treat cancer is not new. It was first explored by a 19th century surgeon, William Coley. While working at Memorial Hospital in New York City, Coley came across a strange case. A patient whose tumor seemed to vanish of its own accord after a serious infection.
Coley thought, there's a power here. We don't know quite how to harness it, but I'm going to try to infect people who may have this kind of dire, inoperable form of cancer and see if we can do anything about it. And that, in a messy and unscientific way, was the birth of kind of cancer immunotherapy.
Coley made a compound of infectious bacteria and injected it directly into the tumors of patients, hoping to trigger a fever that would somehow overwhelm the cancer. Some of his patients were cured, but no one was able to duplicate his results. And for decades, immunotherapy remained on the fringes of cancer research. Even when scientists were able to detect mysterious particles that appeared to be fighting cancer cells.
We noticed these peculiar little bodies with the cancer cells.
We don't know just what they are, and we don't know what it means, but once the cancer cells develop these spots, they go on to disintegrate and die. Well, that's it. That's what we've been seeing. The little dots may be evidence of an immunological mechanism, or they may be something nonspecific, and we hope we can find out with further study.
Immunotherapy remained a backwater. But a few scientists, certain that there was something to it, kept the field alive. One of them was Steven Rosenberg, who, since the 1970s, has been exploring immunotherapy treatments at the National Cancer Institute. A surgeon like Coley, he too had had a patient whose cancer had miraculously disappeared.
All aspects of his cancer were gone. He had undergone one of the most rare events in all of medicine. He had had a spontaneous regression of all of his metastatic cancer.
Rosenberg believed that the explanation had to lie in the patient's own immune system. He decided then and there to focus his research on immune cells, or lymphocytes.
Okay, let's talk about admissions for this week.
The body has hundreds of billions of lymphocytes. And somewhere in the body of a cancer patient, there are lymphocytes, we hypothesized, that could recognize what was different about the cancer.
So Mark, let's hear about cells.
We have Cermak on the NMA arm of the randomized protocol. Let's do start infusion.
It was that hypothesis, it was that dream that then led us to try to identify the actual cells that were attacking the cancer and use them to actually develop a cancer treatment.
Rosenberg isolated various types of immune cells in his lab, and in a series of clinical trials, injected them into patients. But progress was painfully slow. In the first 66 patients, his therapy showed no signs of working. Then, in 1984, he treated the 67th, a Navy officer named Linda Taylor, with a far higher dose. 3 decades later, she is still in perfect health.
Oh. I tell you, I never cry except around you.
It was an important event in the development of cancer treatments because it showed people that it was possible, at that point in a very tiny percentage of patients, to cause the immune system to make a cancer disappear.
The hope from those early experiments was that if you could somehow activate specific aspects of the immune system, could you now educate it to attack a cancer cell and not attack a normal cell?
Rosenberg went on to discover that a specific type of immune cell, called a T cell, was active against some cancers, but when greatly outnumbered, was too weak to defeat them. Through dozens of experimental trials, he learned to extract these cancer-fighting T cells from a patient's own body, grow them in the lab into a vast army, billions of cells strong, and then infuse them back into the patient's body to fight his or her cancer.
So Naomi, you have 68.6 billion cells.
All right.
More than what you thought.
Rosenberg is running several clinical trials for melanoma patients using this approach.
All right, dear.
Right here, little buggers. Right in this area. Choo, choo, choo.
Every week, he sees a new group of patients. all with advanced cancers, most of whom have exhausted every other treatment.
Mr. Rogers, I'm Dr. Rosenberg. Hi, delighted to meet you. Good, please stay right where you are.
I'm Jan.
Hi, Jan, delighted to meet you. Tell me, when did you first notice a problem?
September of 2011.
What did you notice?
The mold.
Doug Rogers is a 60-year-old retired NASCAR mechanic from South Carolina. He found out he had metastatic melanoma when he had a black mole on his leg checked in 2011.
And then right in the concave area where the mole was, a little black crusty place came back up.
The cancer soon started taking over his body.
So show me where the tumor originally started. Where was the original mole that you had?
Right here, so the scar.
I see.
It was
I
right
surely
there.
do. Yes. Okay. Good. You can lie back. What we have to do to perform this treatment is we have to take off one of the tumors, because we have to isolate the immune cells that are actually attacking the cancer. I mean, what better place to find them than within the cancer itself? And we grow them up, and then we give them back to you. And in other patients, we've seen very remarkable disappearance of cancer. So that's what we have planned. I've gone over your x-rays. You'd seem to be a good patient for this.
Now, this might be a little chilly. I'm sorry about that.
2 days later, the team prepared for an operation to remove one of Roger's tumors so they can find the T cells that may be trying to fight it.
So this operation is going to be pretty simple as far as anesthesia is concerned. You got any questions for me?
No, sir.
All right, where are you from? I detected a little accent.
Brooklyn, New York.
That's no accent. That's a drawl.
South Carolina.
We've been together since I was 18. And I'm 55 now. We've traveled down a lot of roads, so we've just got a lot left to do together, and we got to beat this.
Is how you feeling it? I might not remember this part.
This may lengthen his life or even cure him. I can't wrap my brain around being without him. I can't do it. You know, he drives me crazy just like any husband drives a wife crazy, but I can't imagine life without him.
With Rogers still in the operating room, Rosenberg's team delivered a sample of his tumor to the lab.
In the laboratory, one of our technicians is waiting to dissect the tumor into tiny fragments, put those fragments into individual culture wells, and let the lymphocytes grow out of them.
Over the next 4 weeks, Rosenberg's team will nurture Roger's immune cells, trying to turn a few cancer-fighting T cells into an army billions strong. Rosenberg has not been the only scientist investigating the immune system and cancer. In the early 1980s, a scientist at the University of Texas, Jim Allison, began work in the field, even though he was told it would stall his career.
There was such skepticism about immunotherapy in general. I remember as recently as 2004 going to a meeting of cancer biologists and feeling that I probably should wear a helmet and a bodyguard and everything to avoid being abused for having the audacity to say, I think the immune system can take care of cancer.
Allison's idea was very different from Rosenberg's. Instead of trying to boost the immune system, he thought the immune system might somehow be holding itself back from attacking cancer cells.
Everyone was looking at ways to stimulate the immune system. No one realized that there were restraints or brakes. Allison found that a certain protein acted like a brake. So you can remove the brakes, and then the immune system goes to work.
In 1996, Allison developed a compound that could free the immune system to attack cancer. It took him years to find a company that would help him produce his drug. But when Yervoy finally came to market in 2011, the whole pharmaceutical industry quickly took note. Since then, several new drugs have been developed based on the same principle, removing the constraints that prevent the immune system from attacking cancer.
Cancer is a dynamic interplay between patient and tumor. And for many decades, we have concentrated all of our efforts on the tumor part of that interplay. And now I think we recognize that there is a role to be played by focusing on the patient and how this host immune response can be tuned to try and control the cancer.
What makes these new immunotherapy drugs so exciting is that, unlike Rosenberg's highly customized treatment, they can be mass-produced and administered at any hospital.
The fruits of Jim Allison's work move the field of immune therapy to make it generic. And that has tremendous impact. From a financial point of view, you don't need to individualize. You have the same vial for everyone.
For reasons not wholly understood, immunotherapy has so far been most successful in fighting a small group of cancers, mainly melanoma and kidney cancer. For most other types, the cells in the immune system still seem unable to find and fight the cancer. But another novel approach may greatly expand immunotherapy's reach. In Philadelphia, at the University of Pennsylvania, Dr. Carl June has used genetic engineering to give the T cells in the immune system a kind of homing device.
We know the immune system can be around as a form of surveillance and cull out the early tumors. But in most cases, it fails. And it can't really distinguish at all between a tumor cell and normal cells.
The T cells can't see cancer cells. They are completely blind. They will wander right by. You can actually see this under the microscope. They don't recognize the cell as being bad. So we have to redirect that T cell. We put in a new gene into the cell, and that new gene forces the T cell to see the cancer cell. So it's very much taking off the blindfold and allowing the T cell to see the cancer cell.
By re-engineering T cells this way, June is creating a living drug attuned to each patient's cancer. He received approval to try the technique in a clinical trial of seriously ill leukemia patients. At the same time, a 6-year-old girl named Emily Whitehead, who was being treated for leukemia in a nearby hospital, took a sudden turn for the worse.
Our doctor came in and said she has a full relapse. It's very different now, and you know, survival is less than 30%.
We found out that she does have a specific mutation, and the doctor told me not to Google it, not to look up any information on it. And so, of course, I did right away. And I saw that very few people with that specific mutation survive. I mean, very few.
Emily's health worsened by the day, and when the possibility of a bone marrow transplant fell through, the Whiteheads leapt at the chance to enroll their daughter in Dr. June's new trial.
You know, if anything was gonna work, this was gonna be it, because there wasn't anything else left for her. If it didn't work, we probably only had a few weeks left with her.
While Emily's family waited for her immune cells to be prepared, Doug Rogers returned to the NCI to continue his treatment with Dr. Steven Rosenberg.
You guys want to come over and see the lab?
Yes, we're looking forward to it.
Yeah,
all right.
A month after the operation in which his immune cells were extracted, they were nearly ready to be reinfused into his body.
Tomorrow, we're going to give you exactly 1 billion cells. And about 12 hours after you have those cells, they're going to be growing in you, and you're going to have 2 billion cells.
In 12 hours, my body had doubled. I thought it was truly amazing.
Yeah.
I mean, it was so interesting. And then letting me look at my cells under the microscope, it was extraordinary.
It was really emotional, too. I caught myself just fighting back tears. I didn't want to embarrass myself crying over a little thing of Dougie's cells, but I mean, it could mean everything to us.
I mean, if you could have looked under the microscope, you know, all the melanoma dots were gone. It was replaced by healthy cells. And then when you actually letting me hold them.
Look, you can see them all in there if you look carefully. See them all?
You're holding your cells in your hand. It might save your life.
2 billion.
It was extraordinary.
That's a lot of cells. Feel it?
Okay, look this way, Dougie.
Afraid I'm gonna drop.
Don't drop it.
I'm just excited to get them in there and let the cells
Do their thing, huh?
do their work that the doctors designed them to do, hopefully.
The next day, however, there is a problem with Roger's cells. A virus has contaminated them, and they are no longer safe for infusion.
Something very unusual happened to your cells, and that is in the last day, it looks like they're infected. And so our plan is to abort the cell infusion today, of course, and prepare a new batch for you for next week. That's the bad news. The good news is that we have things in reserve.
Can you grow them and prepare them in 6 days?
We can. From everything I understand about what went wrong, we should be able to get you good cells 5 or 6 days from now. Okay?
I mean, obviously we were disappointed, but you can't do anything about it, so you just move on.
You have to dig down deep and find your strength and just be prayerful that he'll stay healthy for the next week while they're growing.
And they were such good, healthy cells, too, they said. But I mean, so will these will be also because they came out of the same batch, so they'll be fine. It might even be better.
Four weeks after arriving at Children's Hospital, Emily's cells were ready. She would be the first child and only the 4th person ever to receive this treatment. And her doctor, Stephen Grupp, prepared to give her the first of 3 infusions.
Emily Whitehead, 55.
This is the stuff that we're actually talking about, and each day the volume goes up. We've only done this in a very small number of adult patients, but how actually well it will work in kids is only possible to know by actually doing it. All right, we're going to get started here.
Why is there 2?
You seeing 2 Rachels? That's all right.
Okay, we're done. That's the whole thing. Yeah.
So we finally got there.
Yeah.
It's a little bit less than we usually give, but this should be enough, and they're very highly potent.
A week after Doug Rogers' original batch of T cells was infected, he was given an infusion drawn from a much smaller batch kept frozen in reserve. It was the first time Rosenberg had ever tried this.
I'd be just lying if I didn't say I'm not terrified. And
You're all nervous.
I mean, sometimes we have those hard conversations now, and I do fine with it until like night comes, and then it's hard.
Hopefully I got a new lease on life. My cells were saying, let's get to work. They're rolling their sleeves up, see. You got a voracious appetite, hopefully. And we envision them as Pac-Man, you know, they're gonna go to those melanoma cells.
Okay.
What's the matter? No, it's fine.
Day 2, we went in and got 30% then. First day was 10%. And we went home, she was on my back doing horsey back rides and felt good. And then at midnight, she spiked a fever. So we drove back to the ER. And then things just spun out of control. And they put her to sleep, you know, and then that was tough, you know, because at that point, you know, Dr. Alexis said, this is as serious as it can get. And then they had a whole team, as soon as they had her under, a whole team of doctors come in. And I suited up with them and put the mask on and everything. And then, you know, watch them cut artery lines in both wrists and then in her thigh. And they cut an artery line in her neck. And when they were done, there was 17 IV pumps keeping her alive.
They came to us and said that they didn't think that she was going to make it through the night. I remember sitting by her bed watching her on the ventilator, and I just kept thinking that this can't be the end. This isn't how it's going to end. It can't be it.
She's as sick as a human being can possibly be. The ICU staff are working flat out to try to keep her alive. We obviously think this is a toxicity of the T cells, but we don't really know what's happening. And so now what?
With Emily's life slipping away, June's team frantically ran another batch of blood tests, hoping to uncover precisely why her new immune cells had turned on her and made her so sick. The tests came back showing skyrocketing levels of an immune protein called IL-6.
When those levels came back, they were literally off the charts. So then I suggested a drug that can block IL-6. That's never been given to cancer patients before, but it is an FDA-approved drug for juvenile arthritis. And it just happens that my daughter has that disease.
Dr. Grupp said, I'm going to tell you, we're grasping for straws, but if we give her this arthritis drug, it could help, because she can't get any sicker or she won't be with us.
There is an enormous role of luck and happenstance in these kind of situations. We gave that drug, and her response was astonishing. I mean, the ICU staff that were on that night say they have never seen a patient that sick get better that quickly.
Emily finally woke up in the intensive care unit on her 7th birthday. After her brush with death, the doctors still didn't know if the T-cell therapy was working. 3 weeks later, they did a bone marrow test. It came back negative. Emily's leukemia had vanished. Emily's close call had threatened the clinical trial, but in the end, dozens of other children with leukemia were treated, and the arthritis drug that saved Emily's life became a standard part of the therapy. Emily was through the worst. But she was entering uncharted territory. As the first child ever to get this treatment, her medical team had no idea how long her new immune cells would be able to keep her cancer at bay.
So in our last 6 evaluable patients, there are 4 complete regressions and 2 partial regressions. So that protocol.
We're in the beginnings of a very long and hopefully exciting road with immunological therapies. There are people who dedicated their lives to this. And finally, we're beginning to see interesting glimmers in which the immune system can be educated to start to see cancers and to kill those cancers.
Right now, immunotherapy remains something of a roulette wheel.
This large one had almost gone away completely, right? What is it like?
Doctors are not sure why it works in some patients and in some cancers, and not in others.
Wow, she's having a fabulous response, isn't he? It looks like everything is virtually disappeared, so we're thrilled for you.
You know, like a little over a year ago, I thought I was gonna die. But you've saved my life, and I just can't tell you enough to thank you just for everything.
In Rosenberg's most recent trial of 25 melanoma patients, 18 saw their tumors shrink, and 9 were still alive after 5 years. But for the others, there was often no further treatment he could offer.
Why don't you measure it, would you?
Looks larger. That one does look larger. It's 40 millimeters up to 48.
The patient comes for this follow-up scan, and for them, this is a life and death visit. If the treatment has not worked, very often there's nothing left to do for these patients.
All right, let's go see.
A month after getting his cells, Doug Rogers is back to see if they were working.
Well, hello again. So nice to see you. Come over here and sit down.
Hi, good to see you.
Well, how have you been doing?
I've been good. Real good, matter of fact.
Tell me what you've noticed about your...
Well, it just looks so much better, but mainly it just feels better. I mean, it feels pretty much like my right leg does. Yeah.
I've been looking at your x-rays, and the x-rays show more than half of all the cancer gone. It's at least a 55% decrease compared to the start on the x-rays, both in the groin as well as in these tissues. So we're really excited about it. So you had these 2 big ones. And those 2 big lesions were these 2 that are now way, way down.
Yeah.
Well, that's really a good sign that things are happening so quickly.
It was for me, but from your standpoint, are you pleased with everything how it's gone?
You can sit up there. Again, when we see this kind of regression at 1 month, it very often continues until everything disappears, but not always. So we're going to have to follow it carefully to be sure it doesn't start coming back and see. So just going to be more thrilled with how things are going. So.
Well, hey.
We are too.
Thank you very much.
Very exciting.
Okay, now wait here, because Dr. Korn, I want Dr. Korn to come in and just go over you a little more carefully.
Okay.
So nice
Thank
to see
you
you
so
again.
much.
So we'll see you in a month.
Okay, yeah, I'll see you in a month.
I'll be here.
Okay.
Absolutely.
All right. Thank you very much.
Fabulous news. 55%.
That's pretty good news.
Good news.
But you got to thank the man upstairs first.
That's right. 55%. That's amazing.
Yes.
Just think if it continues like that, Doctor.
In April 2014, 2 years after she received Carl June's risky gene therapy treatment for her cancer, Emily Whitehead returned to Children's Hospital in Philadelphia for a checkup.
Let's whip this stuff quick. Well, today is Emily's 2 years since treatment. So, you know, we're going to get our blood work checked, and so it's a big day for us.
We're always a little bit nervous because just walking into the hospital and you hear the sounds that we heard for 3 months. There's that big structure, and there's like a dinging, and all of a sudden, you know, it'll hit us all over again.
There's been too many times when we didn't get the right outcome, so it does make us nervous, but we don't expect anything but good results today. How about it, Em? What do you think?
So, how you feeling?
Good.
Any problems?
No.
None whatsoever?
No.
You go to school every day?
Yes.
You listen to your teachers?
Yes.
Okay. How are your grades?
Good.
When we wrote this trial, we said we would follow patients for 2 years. We never imagined that I would actually be able to follow patients for 2 years, but we said that's what we would do. And now we've reached that point. Nice deep breath, son. We'll continue to monitor her situation. We'll continue to watch for the possibility of her disease coming back. But she has completed the treatment. The question you're really asking me is how long do you need the cells to stay in remission forever? And the answer is I don't know.
Yeah.
You know, we're super excited that she's at this point.
We are
but,
too. Yeah.
You know, every day that she goes out from her cell therapy makes her unique. So, you know, the amazing thing is that she's doing as well as she's doing. The nerve-wracking thing is we don't really have the answers on what's going to the next year or 2 years or 10 years look like.
Yeah.
We don't know because she is plowing new ground here. You know, nobody thought we would be in this position when we started.
I have a dog, a bunny, and a fish.
Oh my gosh, you love animals, don't you?
She is absolutely a pioneer. I mean, she was the first kid. She was the first patient with ALL. She was the first patient who got so terribly ill. She taught us about the toxicity control treatment, which has saved this therapy.
All right, so let me set this up real quick. Turn on the light.
We've now treated 30 children and had, 27 of them have complete responses. I mean, they're not lasting in all of them, but it looks very hopeful that there's going to be many more children like Emily. We can't say the C word, cure, yet. We don't know. It's only with more time will we know if every last cancer cell is gone.
We got some results back, and CBC looks good. White count's 4.5, hemoglobin's 12.9, and her platelets are 171, and the differential's okay. So the preliminary look is 2 years cancer-free. So
It's a good day.
it's a great day. Yeah.
So many promising cancer cures have come and gone over the years that many researchers remain cautious about the meaning of this latest development. But results like Emily's have made immunotherapy the talk of the cancer world.
Early results are raising the tantalizing possibility that we may actually be seeing cure. It's too early to tell, because to know you have a cure, you're going to have to wait. But it has that feeling, and I think that's why there's this literally a thrill going through the entire oncology community to see some of these clinical responses to these new immunotherapies.
What was unique in our experience was that most of these responding patients achieved deep or complete responses, with many showing...
We have seen that with targeted therapies, resistance occurs. But here is different. This immune system is not taking any vacation. That immune system is there for the whole trip. The patients that respond to immune therapy, they respond for a long time. And I think that this will change, clearly, the way we treat cancer forever.
It seems unlikely that any one treatment or method of prevention, or all of them working together, will ever eliminate cancer completely. The history of the struggle against the disease, from medieval apothecaries to modern operating theaters, from radiation to chemotherapy, to targeted therapy, and advances in prevention and early detection, all have taught the cancer world the value of tempered optimism. But no one doubts that the great barrier to all cancer therapies, the mystery of how cancer works, is finally being broken down by the concerted worldwide efforts of researchers and doctors and nurses, and by patients. Fresh insights from the Cancer Genome Atlas are revealing in ever greater detail the nature of cancer's complexity, enabling researchers to uncover patterns in the ways it evolves, interacts with the immune system, and thrives inside the human body. This profusion of knowledge is inspiring new ideas for treatment and prevention. While scientists are reluctant to use the word cure, many believe that it is only a matter of time before most types of cancer become manageable, no more terrifying or destructive than any of the other chronic diseases that afflict humanity.
We have entered a time that is incredible.
1, 2, 3.
Our understanding of cancer is really at a point where we have the opportunity to make progress at a rate and a level that we've never seen before.
Hands together. Land right here. Let your arms come straight out when you swing. Say there.
There has been one revolution. That's the revolution in understanding the disease.
Pops gets an at-bat.
The second revolution, which is taking that understanding and putting it to work for us in cancer patients, is a work in progress. It's not going to come quickly. It's not going to come without research. But it's going to come.
You look so pretty. Where are those fingers?
When you look at what's going on with cancer right now, it's stunning. It is exhilarating. I'm amazed that we can, in the course of half a century, go from knowing nothing to understanding a problem, to developing rudimentary solutions, to better solutions, to a whole armamentarium of solutions. If it takes half a century, and if it takes a century, that will still be an amazing triumph. And if it's there for my grandchildren, that's nothing we should be apologizing for.
What I'd like to see you do is first to localize your lesion.
There are critics who've said that we're caught in this perpetual cycle in which we have hope and then despair. But these cycles have moved us forward.
Come back.
The way that we've understood and treated cancer as a biological entity, as a social phenomenon, as a cultural phenomenon, has transformed over the last few decades and will continue to transform in the future.
Fantastic, wonderful.
If the cancer cell is evolving, then so are we.
This program is made possible by Genentech, dedicated to making a difference in patients' lives around the world, and by Cancer Treatment Centers of America, providing integrative treatment for over 25 years. By Siemens, a heritage of innovation, a passion for life. By David H. Koch. By Bristol-Myers Squibb, committed to the science of immuno-oncology. By the Alfred P. Sloan Foundation program to enhance public understanding of science, technology, and economics. By the Kovler Fund, Pursuing Solutions for America's Neglected Needs, by the Arthur Vining Davis Foundations, and by the American Association for Cancer Research, by American Cancer Society, by the Leukemia and Lymphoma Society, by the Entertainment Industry Foundation, by Stand Up to Cancer, by the Corporation for Public Broadcasting, and by the generous contributions to this PBS station from viewers like you. Thank you.